So let's talk about simulating a sine wave. And now we always check our audio before we really get going. So in order to simulate a sine wave, you just add a regular voltage source, and you can click Advanced, where before for a DC value you can put in just your DC value and a series resistance. We have the sine wave function, 0 offset, amplitude of 1, frequency of a kilohertz, and we have a phase component. Now this is in the manual, but maybe not as clear. All right, you can download this file if you like. So in order to run it, you just go Simulate Run, and if you haven't set up a transient simulation, this will pop up, and you just would click Transient, put in 2 milliseconds, and you should see 2 periods of a kilohertz sine wave just fine. If we want to adjust the phase of that, you can put in whatever phase you want, and we can even step it so that you can see the phase changing as we go. And here's another file you can download. Now if we go to a SPICE simulation without the phase, let's just notice some things. So we're going to run it, and there's something that I don't want to show you just a second. Okay, there's the V in we had talked about. Goes up to 1, down to -1, and the period is 1 millisecond. Fine, right? Well, what would happen if we put a sine wave into a low-pass filter? So I'm just going to bring this up, and this was pre-done, if you will. Okay. So these two net names connect it as if a wire was there. These two grounds are like net names. And so we can run it again. And this time we'll also plot V out. And you can see that the peak is changed. All right, in this case, the peak is going by 1. But in V out, the peak is attenuated. And not only that, but it seems to take some delay to make that happen. Now you can put the delay in seconds, or you can calculate what the phase of that is. We're really just going to talk about magnitude right now. So when you do a Bode plot, you put in a sine wave of a certain amplitude. We like to use 1 because it makes the math easier. And we change the frequency. So this one simulation would give us 1 point on a Bode plot. And I say, great. So if I know V in and V out, right, all I have to do is calculate V out over V in, which I pulled off a number of 0.192. I take that in dB, which gives me about -14, right? Sounds good, doesn't it? In fact, I don't have to eyeball it. I can use SPICE to measure during transient something that I want to call V peak and the max of V out. So it's going to pull off this maximum value rather than me having to kind of fool around with a cursor. All right. And I can view that by just looking at the error log. V peak max equals 0.25. So here I kind of eyeballed it at 0.192, but the peak it's telling me is 0.25. Okay. So we can find out what that would be in dB. All right. which gives me minus 11 dB. All right, fair enough. What does a Bode plot simulation say about that? Well, if I simulate the Bode plot, I can put AC analysis entered in. And now this is going to sweep the frequency. What we did before is one frequency. Now this is going to sweep the frequencies. And there's V out. Okay. And we find the cutoff frequency by finding the minus 3 dB point. Or actually, we want to see what happens at a kilohertz. So I'm getting the cursor right on a kilohertz. And I'm going to read off the magnitude in dB. And it's 16, not 11. Does this mean all theory and everything I said for the whole course isn't true? No, it's something that we have to watch out for when we do a transient simulation. So let's go back and go back to the transient. All right, and it might be a little bit hard to see, but I think if I put two cursors on this, all right, we can see there's about V peak of that one. And wait a second, V peak is changing with time. And it can take a while for that sine wave to give us the point that we want. So that's okay. We just will run for 10 milliseconds and see if the sine wave stabilizes. All right, and I can take this here, and I can take this here, and at some point, it's giving the same value. So it starts off high, and then it'll stabilize. So even now, if I run it again, this is still the max value, and that would still be the min. That would be higher than where I would want it to be. So what I can do in Spice is say, hey, stop at 10 milliseconds, go from 0 to 10, but don't save the data until 6 milliseconds. Right? Don't start saving till I get there. And let me rerun it. Now it looks like it's from 0 to 4, but that's because it was 6 milli to 10 milli. Right? And now when I go and look at the measure statement, V peak is 0.157. Which is minus 16 dB, which matched our AC analysis. 1 kilohertz, about minus 16 dB. And now the simulation is matching, both simulations are matching. All right. Now if I change this to, let's say I change the simulation to 10 hertz. Okay. I have to change the frequency to 10. And I have to change the simulation time to 10 seconds. Or no, let's take a second, because 10 hertz is a tenth per cycle. So 1 will give me 10 cycles. And if I start saving after 0.6, I should get, I'm still getting, see how it kind of scales? Notice that V out and V in, just looking at it, are very close, and the phase is small. All right, so there's no phase delay. So at 10 hertz, like I said, if I go back to AC analysis and run at 10 hertz, magnitude is very close to 0 dB, And the phase is, where's the phase? About -3 degrees of phase. We're out here at a kilohertz. We were at -80 degrees of phase. And this dashed line here corresponds to the right axis, and that gives us the phase. So if you wanted to do a Bode plot kind of the long way, you would have a 1 kilohertz sine wave, 1, 2, 4, 1, 2, 3, 4, 5, 6, 7, 8, 10, 20, 30, 100, 200, 1K, 2K, 5K, 10, 20K, 30K, all the way up. And you would just keep changing the function generator, measuring V out and V in, and measuring the time delay, which you can then put into the phase, and you can do that by hand. When you do that function generator, in general, it's happening so fast that you don't have to worry about the signal stabilizing like it does in this numerical simulation.